Welcome to the class. Today we will start acting upon the Brayton cycle. In last class we were seeing about the basics of thermodynamics, and we are now trying to link it with the Brayton cycle. In last class what we had seen was about first law of thermodynamics, its application to closed system, means how to write the expression for first law for closed system. Then we saw how to write the expression for first law for open system. Some points which should be explained here for the first law of thermodynamics when it is concerned with the open system was that in last class we had seen that there is an open system. Here we actually mean that we are dealing with a thermodynamic system. So this is an inlet, this is an outlet, and then there is some Q, and then there is some W. Then we wrote an expression saying that let there be many inlets and let there be many outlets. Then what did we write? That sigma I is equal to 1 to n1, let there be those number of inlets. So expression is Hi plus Vi square by 2 plus G Zi into Mi dot. Mi dot is the mass flow rate through corresponding inlet. Then there will be some heat sources which are associated with the open system. So let there be J. So J is equal to 1 to N2, and then this is equal to, then there will be energy which is going out of the system. For that we said that there will be N3 outlets, and then we have Hp plus Vp square by 2 plus G Zp into Mi m dot p. Then plus there will be Q as an index for work interactions, and then that is equal to N4 WQ. This is the expression for first law of thermodynamics applied to open system. Here in last class it was yet to be explained that what are these terms. This is H is enthalpy, V square by 2 is kinetic energy, and Gz is potential energy, m dot is mass flow rate through corresponding inlet, or maybe m dot p is outlet. So this H plus V square by 2 plus Gz, this energy is total energy which is coming from the inlet and which is going out from the inlet. So this is balance between energy coming from the inlet, energy going from the outlet, and then there are further work and heat interaction. H is basically enthalpy, and enthalpy is internal energy plus P by rho. So we have H plus P by rho plus V square by 2 plus Gz. So this is mechanical energy. This is mechanical energy, and then this is internal energy. So what we are getting in the control volume is internal energy plus mechanical energy summation, which is entering into the control volume and which is also leaving from the control volume. However, further H is represented as function of temperature, like U, which is internal energy, is also a function of temperature, where we know from basics of thermodynamics H is Cp into T and U is equal to Cv into T. Here Cp is specific heat at constant pressure and Cv is specific heat at constant volume. So what we are having is Cp and Cv to be constant for our course, and here only we define something like the gas to be calorically perfect. Suppose I am working with a gas which is said to be calorically perfect. Then what would happen? Basically gas is a perfect gas when it is actually following the equation of state. But then we are further adding one more concept to it as and saying a gas to be calorically perfect. So for calorically perfect we are actually having Cp and Cv are constant. Cp and Cv are constants in a calorically perfect gas. So gamma, which is specific heat ratio, and that is Cp upon Cv, and this is also constant when we are saying that some gas is calorically perfect. We need this concept to be explained or to be used rather when we are going to deal with Brayton cycle calculations. So now we will start with Brayton cycle, which is a thermodynamic cycle. Suppose we have now something as our closed cycle power plant. So we know that in the closed cycle power plant there is first one compressor. So C is compressor, and then from that we will get some mass flow rate inside the compressor. Then we will have some heat exchanger, and that is giving heat to our working medium, and then we have turbine. So this is turbine, this is heater, and we then have a pre-cooler as what we had seen in previous class. So this is a pre-cooler. Now we have to draw thermodynamic cycle for this complete mechanical circuit. We will say that 1 is the state, thermodynamic state at the entry to the compressor, 2 is the thermodynamic state at the outlet to the compressor and inlet to the heater, 3 is the thermodynamic state for the entry to the turbine, and 4 is the thermodynamic state for the exit of the turbine. So first is the process, which is 1 to 2. Process 1 to 2 is isentropic compression. Isentropic compression. Here we practically mean that the compression process is adiabatic and reversible. So the process 1 to 2 is isentropic compression. Since it is adiabatic, there is no expectation that there is heat addition or heat transfer, and then further we are doing process of compression in a smooth compressor where there is no friction loss. So process is isentropic and this is reversible and adiabatic. Then we have process 2 to 3. Process 2 to 3 is isobaric heat addition. Heat addition. So this process, as name suggests, isobaric means constant pressure heat addition process. Then we have process 3 to 4, which is isentropic expansion. Isentropic expansion, process 3 to 4. Again it is similar to compression, that we have isentropic means we have adiabatic and reversible. We expect there is no heat transfer, turbine blades are smooth, there is no loss due to friction, and then there is an expansion process in the turbine. Then we have process 4 to 1, which is isobaric heat rejection. The process of isobaric heat rejection is same as process 2 to 3 where we have constant pressure. So process 4 to 1 also has constant pressure, but it is the process only for heat rejection. So these four processes, these four rather thermodynamic processes constitute a cycle which is the Brayton cycle as the title of this today's presentation. So now we have to draw the thermodynamic cycle for this thermodynamic cycle on the PVTS diagram for this Brayton cycle. So let us first draw a thermodynamic cycle on TS diagram. Let this be the T axis and this be the S axis. We know that T is temperature and S is entropy. These terms are known to us from the basics of thermodynamics. Now we are supposed to draw the process. So here let us draw the process 1 to 2, and then the process 1 to 2 is heat addition, is isentropic compression. So here is the process 1 to 2. We have to keep in mind that a line, since it is an isentropic compression, so what is happening? Isentropic means entropy should remain constant. So this is a vertical line on TS diagram. And then we have next process, which is isobaric process, which is isobaric heat addition. Since it's an heat addition process, we will indicate it as isobaric process. Then this is 2 to 3 is isobaric heat addition. And then we have process which is isentropic expansion. So this 3 to 4 is isentropic expansion. Now we have process which is 4 to 1, and then that 4 to 1 process is isobaric heat rejection. So this process is remaining is 4 to 1. So we have basically we have in this TS diagram we have here as compressor as what we indicated here, and then we have here heater, here we have turbine, and here we have precooler. So heater will give you heat, this is Q heater, and then precooler will reject the heat, this is Q precooler. Here compressor will give W compressor in and turbine will give W turbine out. So this is work and heat interaction in the Brayton cycle. There is one problem while drawing the TS diagram which we generally commit. While drawing the TS diagram, generally what we try to draw is like this. We draw it as T axis, S axis, and then we draw it this way. 1, 2, 3 and 4. If we draw it like that, where we are drawing it as a parallelogram, then there are two problems. One is we are drawing this line 2 to 3 as a straight line, and it is not true. Line 2 to 3 is a curved line, as you can see over here. And why it is a curved line? We can know from first law of thermodynamics, that is dq is equal to dh minus vdp. What is line 2 to 3? Line 2 to 3 is isobaric heat addition. So isobaric means this is 0. So we have dq is equal to dh. But if we combine first and second law, then we can say tds is equal to dh. But as what we have seen just in previous slide, that dh h is equal to Cp into T, so dh is equal to Cp dt. So dt by ds at pressure constant, we get it as T upon Cp. So T upon Cp is slope of isobaric line on TS diagram. Now by addition of heat, temperature is increasing, so slope should also increase. So line should be the red line what we have drawn on one side, and it is not this kind of line. So this is wrong. So further, these two lines 2 3 and 1 4 should not be, rather process 2 3 and process 4 1 should not be parallel to each other. Since temperature at 2 is higher, so it should have higher slope to start with, or it has rather different temperature than 4. That is why their slope should be different to start with. Further, from 2 temperature is increasing, so slope should increase. From 4 temperature is decreasing, so slope should decrease. So if we draw a parallelogram like this, then we are committing mistake for drawing the TS diagram. So having said this, now we know how to draw the TS diagram for the Brayton cycle. Having said this, we can now draw TS diagram. Once TS diagram is done, we can now draw HS diagram for the Brayton cycle. Now in case of HS diagram, we have, again we will first draw the axis which is H axis and S axis. We have H, which is enthalpy, on Y axis, and we have S, which is entropy, on X axis. HS diagram also gives us a representation which TS diagram would also give, but at the start it is necessary to draw the diagram in all sense. So we have first process 1 to 2, process 1 to 2, which is isentropic compression. Then we have process 2 to 3, which is in red color. So that is process of isobaric heat addition. Then we have process of isentropic expansion in the turbine. We have isentropic expansion in the turbine, and then we have precooler, which is heat rejection process. So we have 1 to 2, so then we have 2 to 3, and we have 3 to 4. So this is what our HS diagram. Representation of HS diagram and representation of TS diagram will not be different. They would look similar curves, but only difference would be the slopes. And what is that difference? As we have seen, dt by ds at constant pressure for TS diagram is equal to T upon Cp. If we go back, we got this expression from TdS is equal to dH. Here we can know now that dH by ds at constant pressure is equal to T. So slope of constant pressure line on HS diagram is equal to local temperature. So local slope is dependent on local temperature. So Cp is always greater than 1. So what would happen? T upon Cp is the number which will be lower than T. So slope will be higher on HS diagram in comparison with TS diagram. So having said this, now we will draw the next curve, which is PV diagram for the Brayton cycle. So in case of PV diagram, we have again axis which is P and V. V is volume, specific volume, P is pressure, and now we are supposed to draw the PV diagram. But first process is compression process. So in the compression process we have increase in pressure, so we have to keep it in mind. So process 1 to 2 is increasing pressure. So process 1 to 2. Process 1 to 2, which is isentropic compression. Then we have process 2 to 3, which is again process of heat addition. So we have process, but that is isobaric process. So as name suggests, it is an isobaric process, so pressure should remain constant. Y axis is pressure, so it has to be a horizontal line. And then we have isentropic expansion. So the process is isentropic expansion. Isentropic expansion 3 to 4. And now we have last process, which is heat rejection, and then we have 4 to 1 as heat rejection. So this is PV diagram for us in case of Brayton cycle. So now we have drawn TS diagram, HS diagram and PV diagram for Brayton cycle. Now we will try to do the basic calculations for Brayton cycle. Here one more thing we should remember, that if instead of having the open cycle gas turbine power, closed cycle gas turbine power plant, we can have open cycle based gas turbine power plant also. So if there is an open cycle gas turbine power plant, then process 4 to 1 practically is not existing. But instead of that, we pretend that there is a heat rejection to the atmosphere, and from atmosphere we are taking same air of same mass flow rate, but at the temperature which was at the inlet of the compressor. So there is no practically 4 to 1 process in open cycle gas turbine power plant, but it also runs on Brayton cycle, as we can see for the closed cycle gas turbine power plant. Now having said this, we will start with the calculations for the Brayton cycle. Now I will redraw for all sake the TS diagram for Brayton cycle. Now this is T axis, this is S axis, and we drew like this. We have 1, 2, 3, 4. These are the 4 processes. Now let us try to find out what is first the heat and work interaction in each process. So let us see for process 1 to 2. For process 1 to 2 we have isentropic compression. So process 1 to 2. Since we are saying that process 1 to 2 is isentropic compression, then we have Q, which is heat interaction in 1 to 2 is 0. Since we say that process is isentropic, so process is reversible and adiabatic. So Q12 is 0. Now only what we have to do in process 1 to 2 is find out work interaction. So how to find out work interaction? So now we can apply the steady state energy equation for, or steady flow energy equation what we had derived for the compressor. So as per the steady flow energy equation, and with the fact that compressor has only one inlet and only one outlet, we have H1 plus V1 square by 2 plus GZ1 into m dot plus Q plus Q12 is equal to H2 plus V2 square by 2 plus GZ2 into m dot plus W12. But here Q12 is 0. Further, we will neglect, for the sake of simplicity, the change in potential energy between inlet and outlet of the compressor. Further, we will also neglect change in kinetic energy between inlet and outlet of the compressor. Basically, this neglection has a reason that the term H is much greater than the kinetic energy and potential energy terms. So this H is sufficient for us to give the work output or work input. That is why we have H1 into m dot is equal to H2 into m dot plus W12. Now we will write it as H1 is equal to H2 is equal to W12. Now this W12 is a specific work output, means W1 here W12 has units of joule, but here W12 has unit of joule per kg per second. Okay, this is per unit mass flow rate. So this is what specific work output. So we were interested in finding out W12 and we got it as H1 minus H2. But H1 is lower than magnitude of H2, so this term is negative. And we should have expected it, since W12 in case of compressor is the work absorbed by the system. So work by the convention, work absorbed by the system is negative. So we will take for the sake the modulus of W12 and it is H2 minus H1. So this is the calculation equation 1 and equation 2. Equation 1 gives us heat interaction for the compressor and equation 2 gives us work interaction for the compressor. Now we have process 2 to 3. Process 2 to 3 is the process of constant pressure heat addition. So as the process indicates, it is a heat addition process, but it is a non-work interaction process. So W23 is equal to 0. Again we have to find out Q23. So to find out Q23, we will again take help of steady flow energy equation. So we will say that H2 plus V2 square by 2 plus G Z2 is equal to, into m dot plus Q 23 is equal to H3 plus V3 square by 2 plus G Z3 into m dot plus W23. But we know W23 is 0. So what we have is this expression. But again we will neglect the change in potential energy at the inlet and at the outlet, or between inlet and outlet of the combustion chamber or the heater. We will neglect the change in kinetic energy between the inlet and outlet of the combustion chamber. Then we get H2 into m dot plus Q23 is equal to H3 into m dot. So we will specify it as Q23, which is heat added per unit mass flow rate, and then that is equal to, or per unit mass. Okay, there is slight correction here, as we know that unit of W is joule, but here we have m dot which is kg per second, and then this H is in joule per kg. So unit of W12 is joule per second, and then that is watt. So unit of W12 will become only joule per kg. Okay, so here unit of W12 is joule per kg and unit of capital W12 is watt. So similarly, now we will come back here for the process 2-3, where we say that now Q23 is equal to H3 minus H2. Same way here also we have Q23 capital, and that has unit of W, which is watt, which is joule per second, and unit of small Q23 is joule per kg. So we say that Q23 small is a joule per kg heat added into the system. So there are some more things for the rest of the processes. Similarly, for process 3 to 4. For process 3 to 4, we have isentropic expansion. So in case of isentropic expansion, everything will go same as process 1 to 2. Here also we have Q34 as 0, and we here will have H3 into m dot is equal to H4 into m dot plus W34. This will be the work interaction. So we will say that W34, which is small w, which is joule per kg, it is equal to small h3 minus small h4. Okay. So here we get equation, if we remember, then equation 3 here for work interaction in 2-3, equation 4 here for heat interaction in 2-3, then equation 5 here for heat interaction in 3-4, and equation 6 here for work interaction in 3-4. Now we have process 4 to 1. So in the process 4 to 1, it will be again similar to process 2 to 3. It's a isobaric heat rejection. Since it's a heat rejection process and non-work interaction process, W41 is equal to 0. This is equation number 7. And now we will have H4 into m dot plus Q41 is equal to H1 into m dot. So we will have Q41 is equal to m dot into H1 minus H4, or Q41 is equal to H1 minus H4. One more thing to remember over here, that Q41 is a negative quantity, since it is a heat rejected from the system, since H1 is lower than H4. So practically, if I want to find out Q41, I will say that I will take modulus and say that it is H4 minus H1. Now we got such 7 and 8 expressions where we can know the work and heat interaction for the Brayton cycle. Now we will use those expressions for further calculation. So what was our first expression? We have W12 is equal to modulus W12 is equal to H2 minus H1. But we know H is equal to Cp into T, and we know that we are using calorically perfect gas. So Cp into T2 minus Cp into T1. So modulus W12 becomes Cp into T2 minus T1. So knowing the temperatures at the inlet and at the outlet of the compressor, we can find out work interaction. Then we have Q12 0. This is for compressor. Now we here this whole thing is for compressor. Now for turbine or for heater or combustion chamber, we had seen that Q23 is equal to H3 minus H4. Sorry, it is H3 minus H2. So again Q23 is equal to Cp into T3 minus Cp into T2. So Q23 is equal to Cp into T3 minus T2. So knowing the temperatures at the inlet and at the outlet of the heater or combustion chamber, we can find out heat interaction in the combustion chamber, since we only have heat interaction and work interaction is 0. So this is for heater or combustion chamber. Now we have turbine. So for turbine we have W34, and then that is equal to H3 minus H4. So W34 is equal to Cp into T3 minus T4 as what we got it for compressor. Similarly, Q34 is equal to 0, and this whole thing is for turbine. Now we have the similar expression for pre-cooler or heat rejection process. So heat rejection process, we have Q modulus Q41 is equal to H4 minus H1, and so modulus of Q41 is equal to Cp into T4 minus T1. Then we have W41 is equal to 0, and whole this thing is for the pre-cooler or heat rejection process. So now we have derived the basic requirements for the gas turbine power cycle. This we can use for further calculations of gas turbine power plant. Now what we can need to find out is what are the basic governing parameters for the gas turbine power plant, and if we know their values of the governing parameters, we should be able to find out the rest of the quantities of the gas turbine power plant. We practically mean that suppose we know few things of the gas turbine power plant, and now using those things I should calculate what are the values of pressure, temperature and other quantities at all corners of this cycle. So what are those governing parameters for the Brayton cycle? So those governing parameters for the Brayton cycle are pressure ratio, and that pressure ratio is P2 by P1, which is P2 is the pressure at the outlet of the compressor, P1 is the pressure at the inlet of the compressor. So that pressure ratio is a governing parameter. Apart from that, we have governing parameter as gamma, which is specific heat ratio. We further have governing of the gas turbine power cycle dependence on inlet temperature and maximum temperature what cycle can sustain. So if we know these conditions, then we can find out the properties or the pressure and temperature at all corners of the cycle. So we can do this exercise here onwards. Knowing these values of the governing parameters, we can find out the properties required at all corners of the cycle. So we will do this calculation, and we will also do the calculation or derivation for the performance parameters like efficiency, net work output for the Brayton cycle in the next class. Thank you.